So, gentlemen, so we are going to talk about angular momentum today. Suppose you have a particle and the force F is acting on the particle. So, what is the Newton's second law? This force is equal to mass into acceleration of the particle. Now, what is your acceleration? Time derivative of the velocity. If I take a dot product of this force, this equation with velocity vector, what will I get? If you look at this expression on the right hand side, I take the derivative of this term with time. What will I get? Half m is a constant. You see, half m is a constant, and you apply product rule of differentiation to this term v dot b. What do you get? V dot dv by dt plus dv by dt dot v. So basically, what you get is m v dot dv by dt. So f dot v is equal to time derivative of half mv square. So this term is known as kinetic energy of the particle. What is f dot v? Look at this. Is the trajectory of the particle. Force F is acting on the particle. And during time dt, the particle goes from position 1 to position 2. So particle suffers a displacement dr. This displacement is dr as it goes from position 1 to position 2. So what is the work done during this time? Basically, a force applied during this interval, dot product with the displacement of the particle. This is the work done.
Yes, sir.
This amount of work done, you can call it differential work done during the time interval dt. If you divide it by dt, you get f dot v. So this is your, what is time derivative of work done? It is power. Rate of doing work. by force F. So what is the if you want to find the change in kinetic energy during the time interval 1 to 2, how will you find? D by dt is equal to half mv square. This is equal to F dot. So rate of change of kinetic energy. So d by dt of half mv square is equal to, so whatever is the power supplied, it is used to change the kinetic energy of the particle. So if you integrate half mv square, so this is the change over time period 1 to 2. If you integrate, what will you get? So power integral over this time period 1 to 2, from T1 to T2. Then it will be a change in kinetic energy. Whatever is the energy supplied to the, whatever is the energy supplied to the particle during this time interval, whatever is the work done on the particle during this time interval will go to change the kinetic energy of the particle. So F is the net force on the particle. That net force is imparts energy to the particle, and that change in energy is change of kinetic energy. Similarly, we have the concept of angular momentum. Or rather, first we can talk about linear momentum. So you know force is equal to mass into acceleration, Newton's second law. You can say m dv by dt. So you can say f dt. You can take the dt on this side, m dv. This integral you do over time period 1 to 2. So this term is known as impulse. Impulse provided by this force during this time interval, and this will be equal to, you see, integral of dv is v. So this is change of linear momentum. So impulse tells you how much will the change in linear momentum. You have integrated the impulse, the force applied over time period dt, f into dt over the time interval, and that gives you change of linear momentum. Another way you can look at it is, we have f is equal to, you can say d by dt of m into v. Since m is a constant, you can take m inside the derivative sign. For Newtonian mechanics, m is a constant. Mass is not neither destroyed nor created. It doesn't change, it doesn't depend on the reference system. And this term mv is known as linear momentum. You can represent it by term p. So this is Newton's second law, as you know. force applied to a particle is equal to time derivative of its linear momentum. Now we will talk about angular momentum. So if again you take a force on acting on a particle, you can take a position vector of point A where your particle is. Now we can define as movement of this force. What is movement of this force? Is equal to r cross f. We have already discussed it. You take any point, you have to take a reference point. So, for example, we take reference point at the origin. The left, we have to take the vector from the origin to any point on the line of action of force. We take it as a point where the force is applied. So r cross f, this becomes the movement. Now you know r cross, we can replace f by m dv by dt, Newton's second law. Or we could have directly done it d by dt of linear momentum. Now we can replace it with d by dt of r cross m. If you expand this term, it is dr by dt cross mv. I am using product rule of differentiation plus r cross m dv by dt. So this term is nothing but velocity cross mv plus r cross d by dt of mv. So this is nothing but zero. The cross product of a vector with itself is zero. As the angle between them becomes zero and sine theta of zero is zero.
सर एक क्वेश्चन था सर, यहाँ पे सर जब हमने एफ को एम वी किया तो सर ये बाहर डी बाई डी टी कैसे आ गया?
Yes, here.
सर यस सर दिस एम वी, देन सर ये तो एम वी पे डी बाई डी टी था, देन सर ये आर क्रॉस एम बाय आर क्रॉस अंदर कैसे आ गया सर? वो तो सर वो नहीं है.
Yeah, I have explained it here. This is same as this. So I am explaining it here. If you just take its time derivative, what it is? You have to apply product rule of differentiation. dr by dt cross mv plus you take r stays as such cross d by dt of mv. Any problem?
ओके सर.
So this term is v cross mv. So this is going away. So you see, movement of the force about the origin is equal to movement of the linear movement. Okay. Is equal to d by dt of r cross mv, and this is called angular momentum of the particle. we define a vector L, which is as L is equal to R cross MV. So this is movement of the linear momentum, or this is called angular momentum of the particle. So time derivative of angular momentum of the particle is equal to the torque or moment of the force. And we are taking angular momentum also about the same reference point O, like torque. So here O is a fixed reference point. O is the origin of the fixed coordinate system. So this is a fixed coordinate system, and we have taken the movement of force about this origin, as well as movement of the linear momentum about this origin, or angular momentum of the particle about this origin. So if we say angular momentum is conserved, it means torque applied is zero. Okay. Similarly, if we say linear momentum is conserved, it means force applied is zero. If your linear momentum is conserved, it means dp by dt is zero. Your linear momentum is not changing. It means external force applied is zero. Net force is zero. So these are a conservation law of momentum, conservation law of angular momentum, similarly conservation law of energy. Okay. So now we will go to the rigid body. Till now I talked about a particle. Now I want to find angular momentum of a rigid body. How will we go about doing it? Any idea? So we have a rigid body. We will take its angular momentum about its center of mass. We can take it about any other point. Now we know we can represent general rigid body motion as translation of a reference point and rotation of the rigid body about the reference point. So you have a fixed coordinate system. You represent the position vector of the centroid of the body with respect to this coordinate system. So you can split the motion by using Chaser's theorem into pure translation. And pure rotation. So you, for example, take the reference point as centroid. It can be any other point. Choosing centroid makes your equations of motion simpler. Now, this is the center of mass. If you take any other particle, we can find relative motion between the center of mass and this particle. Suppose this particle is I. So, what is the velocity of this particle I with respect to the velocity of center of mass? So center of mass is called point G. Now velocity of point I with respect to point G will be, suppose this is the angular velocity of the body omega. Angular velocity is a free vector. One rigid body has only one angular velocity at a point of time. It doesn't depend on the choice of reference point. So this is angular velocity. The velocity of point I with respect to point G is omega cross, so position vector of the point I with respect to point G. So you can say Ri. So here I am measuring from point G. So this this vector R is measured from point G. It is a vector from G to I. So this is relative linear velocity of particle I with respect to particle G. So what is the absolute velocity of the particle? So it becomes velocity of G plus velocity of I with respect to G. So you get the absolute velocity of the particle with respect to this fixed coordinate system. Now we want to find angular momentum of particle I with respect to point G. So what will be that? Ri cross mass of the particle mi, absolute velocity of the particle I. So this is angular momentum of particle I with respect to point G. Any problem with this? So you can call it absolute angular momentum. So we have taken absolute velocity of point I, particle I. Now if we sum it over all the particles, sum over all particles of the body, so what you will get? Total angular momentum. Angular momentum of the body with respect to point G. So it is just an addition process. So let's call it vector L with respect to point G. Angular momentum of the body with respect to point G. G is the reference point. Summing over all the particles of the body. Hmm. If I find its time derivative, what is its time derivative? Okay. So we have to engage in a kind of an integration. Any ideas how to integrate it over the entire body? We know the answer. We are looking for something called I omega. Okay. How do I get I omega? So first we have to replace this velocity with respect. So this velocity is nothing but velocity of centroid plus omega cross Ri. This Ri is measured with respect to point G. So this is absolute velocity of the particle. Absolute velocity means measured with respect to the fixed coordinate system. So this is nothing but velocity of the centroid plus relative velocity of the particle with respect to the centroid. So now what we can say, Ri cross MIVG. So I am just using distributive law. So vector product over addition. So it follows the distributive law. Any problem with this? So you see here, Mi is a scalar. You can call it Mi, Ri, Vg is only one quantity. It is constant. It is the velocity of the centroid. It is absolute velocity of the centroid with respect to the fixed coordinate system. So what is sigma MIRIG? So this will be the basically centroid of the body. Now Ri is the you are finding the distance from the centroid of each particle. So this movement should be zero. Do you agree? You are finding the movement with respect to the centroid. So first movement of inertia with respect to the centroid will be centroid itself, and since you are making the measurement from the centroid, this will give you a zero value. So this summation is over all the particles. How you can go about it? So one simple way of going about is I had done it in one way for kinetic energy. So there's triple product was converted into some simpler terms. Now I will do it in a so at that time I had used tensorial approach. This time I will use a simpler approach so that everybody follows. How it can be done easily? So first let us pick one term at a time. Omega cross Ri. So I am not using the term G. So we all know that it is from point G. Measurements are made from point G. So this omega we can write as omega x, omega y, omega z. This is my vector. I take a cross product with Ri. Ri is nothing but xi, yi, zi. So all these x, y, z are measured from the centroid. If you look at the cross product, what you get? So I am just expanding it now. So instead of omega y, I will rather call it omega 2. It may create a confusion. Any problem with this? Just expanded this determinant. Now I need Ri cross omega cross Ri. So Ri is nothing but xi, yi, zi cross the above vector, whatever we just calculated. Okay. So if you just expand it again using the determinants, so you got xi, yi, zi, and this is nothing but omega 2 zi, omega 3 yi, sorry, omega 2 zi minus omega 3 yi. Here you will have omega 3 xi minus omega 1 zi. Here you will have omega 1 yi minus omega 2 xi. So this we have to expand now. So what do I get? This yi will multiply with this omega 1 yi square minus omega 2 xi yi. Then this is minus z xi omega 3 plus omega 1 zi square. Then again you have minus j. You expand this. So omega 1 xi yi plus omega 2 xi square minus omega 2 zi square plus omega 3 yi zi. So there should have been a minus sign here. You see, this was omega 1 yi xi minus omega 2 xi square. Plus k. What is this k? So what you got? Omega 3 xi square minus omega 1 xi zi minus omega 2 yi zi plus omega 3 yi square. So this is what you are getting from Ri cross omega cross Ri. And then you also have to multiply with an mi. So what you will get, if I write as I, everything multiplies with mi and you have to add it up. Okay. So I can define it as omega 1 mi yi square plus mi zi square. This is multiplying with omega 1 minus omega 2 mi xi yi minus omega 3 mi xi z. So this is your ith component. What is your jth component? Plus j omega 2 mi xi square plus mi zi square. You see there are two minus signs. This they become plus with this minus sign. Minus omega 1 mi xi yi minus omega 3 mi yi z. Similarly, you have the kth term. What it is? Omega 3 xi mi xi square plus yi square minus omega 1 mi xi zi minus omega 2 mi yi zi. So I have done it in a long hand. So it takes time, but then you will have a clarity what is happening. So what is this term? You are adding it over all the particles. So this is nothing but your Ixx. What is this term? This is nothing but your Ixy. What is this term? So with a minus sign. So this is, we call the entire thing Ixz omega 3. Similarly, you have got this term. This is nothing but Iyy omega 2. This is Ixy omega 1. Iyz omega 3. Similarly here Izz omega 3, Ixz omega 1, Iyz omega 2. So angular momentum of the body, can I write like this? Angular momentum of the body is equal to some inertia tensor I into omega. And what is your omega? Omega x, omega y, omega z, same as omega 1, omega 2, omega 3. And you have to multiply with the inertia tensor. What is the inertia tensor? Ixx is here, Ixy multiply with omega y. This was your Ixz. It multiplies with omega 3. Then you have got this term Iyy omega 2, or this becomes Iyy. This is your Ixy. This is your Iyz. Similarly, you have got this term. This was your Izz. This is your Ixz.
सर ये
This is your
आई एक्स
Iyz.
के नीचे आई वाई एक्स नहीं होना चाहिए?
Where?
सर ये आई एक्स एक्स के आगे आई वाई एक्स नहीं होना चाहिए?
Okay. Look here, Ixy and Iyx are same.
ओके
This is
सर.
a symmetric matrix. So I have not been very careful with your indices. I could have made it Iyx. Okay. But since it is a symmetric matrix, this product Xi and Yixi is same thing. It's a scalar product which is commutative. Okay. So what is there, that we have found angular momentum as a product of inertia matrix or inertia tensor, we call it, multiplied with angular velocity vector.
Hello, sir.
Yes.
Sir, what about the minus sign?
Yeah. Minus sign is incorporated in Ixy. For example, you have got Ixy. You can say this is equal to minus xy dm. So what I had done? Sigma minus mi xi yi. So minus is inside this product moment of inertia.
Okay, sir.
Okay. All product terms are having a negative sign with themselves. So that's the way we define it in rigid body mechanics. So you have got your angular momentum. Earlier you had seen this term L is equal to I omega. So there you are treating all terms as a scalar. So while you know this is a vector, this is a vector, and this term was treated as a single term, like a scalar term. While here I have taken this as a tensor of order 2. So I is a tensor of then I had told you that we can find principal movements, principal axes. So principal axes are found by solving the eigenvalue problem. So if you take a coordinate system aligned along eigenaxis, suppose you have this body. So you have one coordinate system like this. One you take aligned along the eigenaxis. So then you will not have any product movements of inertia. For example, if you take a body like this, symmetric body, and this is your axis of symmetry, and if you take a particle here at position xy, then you will find there is another particle at position minus xy. And if you try to take the product mi, xi, yi, you know whenever for each xi, yi there is minus xy also, which will knock it out. So your product movements will become zero because you have chosen your coordinate system in such a manner that Ixy becomes zero. So such axes are called principal axes of inertia. So once you have that kind of a situation, you can have your movements of inertia like this: I11, I22, I33. All your off diagonal terms become zero. So this is for this coordinate system 1, 2, 3. These are your axes, and these are your principal axes. So, this is for this coordinate system 1, 2, 3. These are your axes, and these are your principal axes. Okay. So these are the principal axes of inertia. Now you are measuring your angular momentum, your angular velocity, your angular momentum with respect to this principal axis. So you have to represent all your vectors with respect to this principal axis. Suppose this is your body and you found your principal axis like this. While your fixed coordinate system is this. So they are not having the same orientation. Now you will find whatever is the angular velocity vector, you will find in 1, 2, 3 system. So what is your angular momentum? Your moment of inertia axis, tensor, and your angular velocity. Now everything is with respect to your principal axis. So you are measuring with all measurements are with respect to this coordinate system. Now if you expand it, what you will get? I11 omega 1. Basically you are multiplying this diagonal matrix with this. I22 omega 2. I33 omega 3. Can you see this? If you multiply this vector with omega 1, omega 2, omega 3, what you will get? I11 omega 1, other terms will multiply with zeros. I22 will multiply with omega 2, I33 will multiply with omega 3. So this is what is you are getting. So can you say that angular velocity and angular momentum have the same direction? Can you say that? They will have the same direction if I11 is equal to I22 is equal to I33. So vector L and vector angular velocity have same direction. If all principal moments of inertia are equal, or is there any other situation where you can have same angular velocity direction and same angular velocity direction? Suppose your I is only about one axis. You are having angular velocity of the body only along one central principal axis. Now then what you will get? I11 omega 1. So you see these two vectors are in the same direction. So this is the what you were using earlier in your 12th standard. That L is equal to vector L is equal to I omega. So here you are taking your I as a scalar. In this case, I is nothing but I11. You could have taken and body could have been rotating about your second axis omega. So your L would have become I22 omega 2. If your body was rotating about your axis 2. Any doubts? So I have told you what is angular momentum, how it can be found, a general expression for angular momentum for a rigid body. So we saw that it is found using moment of inertia tensor and angular velocity, and we are finding the moment, for example, initially about the centroid. So here this is also about the centroid, and angular velocity is a free vector. It is the same about any reference point. A rigid body has only one angular velocity. So we get this, and then we also had found that moment of the force applied to this rigid body. Find all the forces on the body, take their moments, take the moments about the centroid, So these are the forces acting on the body at position I. You sum all the forces and you are measuring everything. So your measurements are with respect to the centroid of your position vector R. This we had found was this was equal to dl by dt. And while L was this. So we'll carry on with it in the next class. Any questions? So basically I have introduced to you the term angular momentum and we found it for a rigid body. Next time we will see how we will use it in solving our rotational equation of motion. Okay, and we'll see how what is that rotational equation of motion. And there is something called Euler's equation of motion. We will be seeing that. Okay, class is over.